Comparing regression models is one of the most misunderstood tasks in applied statistics. Researchers often pick a model, run it, and then compare its parameters to another model as if they were measuring the same thing. They are not. In this video, brought to you by 3D Statistical Learning, we break down 5 critical principles you must understand before comparing any regression models. Principle 1. Smoothing is a modeling choice, not a truth. When you fit a regression model, you are making choices, whether you realize it or not. One of the most consequential choices is how much smoothing your model introduces. Smoothing refers to how much your model averages out local variation in the data. A simple linear regression imposes maximum smoothing. It forces a straight line through the data. Generalized additive models, splines, kernel smoothers, and Loess curves allow the relationship to flex and follow the shape of the data more closely. There is no universally correct amount of smoothing. More smoothing reduces variance but increases bias. Less smoothing reduces bias but increases variance. This is the classical bias-variance trade-off, and it sits at the heart of model selection. The right choice depends entirely on your objective. If your goal is interpretation and inference, you may prefer a parametric model with more smoothing. If your goal is prediction, you may prefer a flexible model that captures nonlinear patterns. Never choose a model based on what looks smooth or complex. Choose based on what your research question actually demands. Principle 2. Parameters are not comparable across models. This is perhaps the most dangerous misconception in applied regression. Researchers frequently fit 2 different models and then compare the coefficient on the same variable across both, concluding that the effect is stronger in one model than the other. This reasoning is almost always wrong. A beta coefficient in ordinary linear regression represents the expected change in the outcome per 1 unit increase in the predictor, holding all other variables constant. In logistic regression, the coefficient is a log odds ratio. In a Cox proportional hazards model, it is a log hazard ratio. In a mixed effects model, the interpretation depends on whether you are looking at fixed or random effects, and whether you used marginal or conditional specifications. Even within the same model class, parameters are incomparable if the models differ in covariates, link function, scale, or distributional assumptions. A parameter estimated without adjusting for a confounder is not the same as one from a fully adjusted model, even if the variable name is identical. Before comparing parameters across models, ask yourself whether those parameters are even measuring the same quantity. In most cases, they are not. Principle 3. Forget so-called true models. Focus on utility. The statistician George Box famously wrote that all models are wrong, but some are useful. This is not a pessimistic statement. It is a liberating one. It frees us from the trap of searching for the one correct model, because no such model exists. Every regression model is a simplification. It makes assumptions about linearity, independence, homoscedasticity, distributional form, and the absence of unmeasured confounders. None of these assumptions are perfectly true in practice. The question is not whether your model is true. The question is whether it is useful for the task at hand. Utility means different things in different contexts. In a clinical trial, a useful model correctly estimates the treatment effect while controlling for pre-specified covariates. In a predictive algorithm, a useful model generalizes well to new data. In an exploratory analysis, a useful model reveals structure that generates testable hypotheses. When comparing models, do not ask which is truer. Ask which better serves your purpose. Use AIC and BIC for parsimony, cross-validated prediction error for performance, or likelihood ratio tests for nested model comparison when inference is the goal. Principle 4. Holdout validation beats parameter comparison. If your goal is to compare models in terms of predictive performance, the single most important tool at your disposal is holdout validation. This means setting aside a portion of your data before any modeling begins, and using it solely to evaluate model performance after training is complete. Any metric computed on the same data used to fit the model is optimistic. A model with more parameters will almost always fit training data better than a simpler model. Not because it discovered a better representation of reality, but because it memorized noise. This is overfitting, and it leads to poor generalization. Holdout validation breaks this illusion. When you evaluate your model on data it has never seen, you get an honest estimate of real-world performance. Common approaches include a simple train-test split, where perhaps 80% is used for training and 20% for testing, and k-fold cross-validation, where the model is trained and evaluated k times, each time holding out a different subset. Report root mean squared error for continuous outcomes, area under the ROC curve for binary classification, calibration plots for probability models, and the concordance statistic for survival models. Comparing model coefficients without considering out-of-sample performance is an incomplete and often misleading analysis. Principle 5. Use simulations to check parameter recovery, but with caution. Simulations are a powerful but frequently misunderstood tool. The basic idea is, you generate data from a known model, one where you control the true parameters, and then fit your model to see whether it recovers those parameters correctly. If the model consistently recovers the true values across many simulated datasets, that is evidence the estimation procedure is working as intended. This is particularly useful for verifying complex modeling code, for understanding estimator behavior under different sample sizes, for studying model misspecification, and for assessing statistical power. However, simulations only tell you how your model behaves under the exact conditions you simulated. If you simulated data from a normal distribution and your model recovers parameters well, that does not guarantee performance on real data that is skewed or heavy-tailed. Simulations reflect your assumptions. Real data does not always cooperate. Use simulations as a diagnostic tool. Do not treat them as proof that your model is correct for your actual research question. To summarize, smoothing is a subjective choice driven by your objective. Parameters from different models are rarely directly comparable. No model is true, only useful. Holdout validation gives the most honest assessment of predictive performance, and simulations can verify your methods, but cannot substitute for domain knowledge and careful study design. 3D statistical learning. Rigorous, evidence-based, trusted.